Yes, you've heard me right. I am using machine learning to challenge cerebral palsy.
Fold 1 fed the protein sequence and its evolutionary table into its deep neural network, which it had trained to predict the pair representation. And this was the final protein structure prediction.
From a young age, when I visited pediatric doctors, they would deliver a death sentence: brain damage is irreversible. In other words, just accept your fate. But in 2025, DeepMind co-founders Demis Hassabis and John Jumper won the Nobel Prize in Chemistry for discovering the amino acid sequences and three-dimensional structures totaling approximately 200 million. They believe that all human diseases are caused by protein misfolding and abnormal behaviors, and that their approach is actually an application of concepts in machine learning. This news gave me great hope and a strong motivation to try to save myself. I've started rehab at age 1, and my limbs were improving slowly. My best condition was around age 8. At the time, I could practice standing while supporting myself on a table. I could wave my hands to music, and I could play the ukulele and piano with both hands. But at age 14, a sudden burst of tension in my body occurred.
I couldn't take it. I had to cry it out.
This awful tension has been tormenting me ever since. I'm confined and unable to go to school. This situation will last for about 2 to 3 months, after which the tension will gradually subside on its own. This raises an important question: why is my spasticity so quantitative and irregular during my growth? I believe that the quantitative and irregular nature of my tension is due to protein mutations, leading to protein misfolding and motor neuron dysfunction. If I can find a way to alleviate my tension, might I be able to save myself? Save myself? Save myself? I've chosen 6 features that I think are necessary to describe a full protein: leucine fraction, amount of alpha helices and beta sheets, helix ratio, alpha helix secondary structure fractions, and molecular weight. The input is all 6 features compiled into one vector. The output is the probability of mutation in our protein. Because the input vector is in R6, the output vector is in R4, the weight matrix W has shape 4 times 6. So the collection of output vectors are the activation function applied to Wxi plus b, where my activation function is softmax. The training data has size 95, and the testing data has size 5. The loss function is multi-class cross-entropy, so every term looks like y true k times natural log of yk. Choosing max epochs to be 1000, seed to be 62, and the learning rate to be 0.02, I let Python plot the training loss curve shown in figure 2.1. Here the horizontal axis represents the number of training epochs, and the vertical axis represents the loss function. And here in the figure 4.2, I've updated the learning rate to 0.05, and the loss curve is shown here. Now here are the Python testing results. So here every symbol represents the specific mutation at a specific index, and the actual probabilities are one-half vectors. That is 1 in a single component and 0 everywhere else. This represents a definite mutation in one of the codons in our amino acid sequence. Next up, we're going to talk about protein mutation. Now, a protein is essentially a sequence of all of the amino acids. So for each amino acid in a protein, we'll define an injective embedding from amino acids to some vector in R3 that maps every amino acid to a unique vector, where H represents alpha helices, S equals beta sheets, C is the coil. Our training set is the image of all amino acids in our sequence. Here, I'm going to choose the IL6 sequence with the cerebral palsy mutation at the 20th position. We first define the query, key, and value weights as matrices, so WQ, WK, and WB in our D by D, such that D is the dimension of every vector in our input set. Then, for every vector in S, we add the query and key matrix to get the query and key vectors. Then we take the dot product of every qi with every kj. We call these attention scores, aij, and the attention matrix A is the grid of all aij's, where each row is applied by softmax. Attention formula is 1 over root dk times the matrix a1 prime down to an prime, where every row ai prime is the softmax of the original. Putting all aij's in a matrix is identical to computing q transpose k. Now, applying softmax on a row vector ai, we take the exponential of each component, then divide by the sum of every component to squeeze the values in between 0 and 1, obtaining probability distributions. Then we add WB on all of the embedding vectors EI. The output set EI prime is obtained by adding A prime VI, our attention value vectors, to our original embeddings. For j equals 1, 2, all the way down to 15, we'll define the mask vector to be EJ, and the query vector to be the query matrix times EJ. For the key value pairs, we will take the key and value weight matrices and then act them on every single EJ. The attention scores will be the inner products between our query vector and the 15 key vectors, K1 through K15. In order to turn this attention vector into a probability distribution, we apply softmax to it. The input for the fully connected layer is A1 prime V1 plus A2 prime V2 all the way down to A15 prime V15. We will repeat this procedure for all EJs in our amino acid sequence. Here is the attention distribution when our mask vector is E1. The horizontal axis represents amino acid index and type. The vertical axis represents the attention scores when dotted with the query vector. All of the attention weights are in between 0.04 and 0.08. Running our VFC set through a fully connected network gives a new protein sequence, which we'll call Fi, again from I to 15. Now we measure the distance between the output protein sequence Fi with the input sequence Ei. We first define a metric D that takes in 2 amino acids and spits out the norm of the embedding of the first minus the embedding of the second. And this measures the Euclidean distance between the two embeddings, and the autoencoder loss L sub AE is 1 over 15 times the sum from I equals 1 through 15 of the distance from EI to Fi squared. Here, the squared distances amplify the changes and makes it easier to differentiate. However, we can also consider different types of spasticity, such as increased arm tone leg jerking from different protein mutations. The model will be 2 linear layers followed by a softmax, where the output of the first linear layer is the cerebral palsy type, so dyskinetic, spastic, or ataxic. The output of the second linear layer is spasticity type, leg jerking, arm tone, and so on. Now there are more than 2 classes, so we use one hot encoding. The loss is the cross entropy on layer 2. I've built the code in Python with batch size equals 20 and the learning rate to be 0.01. Here are the testing results. There are 5 samples, each with a prediction and an actual. The prediction is the model output, while the actual represents the one-hot encoding on y-test. Ever since I got into studying machine learning, I realized just how useful and applicable it really is. From the YouTube algorithm to self-driving cars, Fortnite robots, machine learning is almost everywhere we look. Here's a scene of me playing Fortnite when I was about 14 years old, getting by the enemy players, okay? Because of my condition, normally walking, brushing, and eating are challenges I need to face. I've held on to a belief. All brain diseases, such as Alzheimer's, cancer, Parkinson's, CJD, are caused by protein mutations in the brain. With this belief, I applied machine learning techniques like self-attention to really understand what's going on inside my brain. As Ashish Vaswani put it, attention is all you need.